In this tutorial, we will be naming tertiary ionic compounds. So we're still dealing with compounds made from metals and nonmetals. However, they tend to contain 3 different elements. When naming tertiary ionic compounds, we still need to determine whether the metal is monovalent or multivalent. And when multivalent, we need to identify the ionic charge of that metal so that that part of the name can be communicated. The second part of the name will be the name of the polyatomic ion, and we don't need to change its name in any way. However, we do need to know how to name polyatomic ions, so you'll see a few examples below. In the first example, we can see that our metal is potassium, which is a monovalent element, and so no need to communicate the ionic charge using Roman numerals or using a classical system. The nonmetal is a polyatomic ion, and we need to be familiar with this ion and know its name. This is called sulfate, and putting the 2 parts of the name together, we get potassium sulfate. In the second example, we have another monovalent metal, silver, and a polyatomic ion that is based on the familiar one, bromate. However, in this example, we can see we have 1 fewer oxygen atoms, and therefore we have to adjust the name of bromate to bromite, and hence the name of this compound will be silver bromite. Example number 3 and example number 4 both use metals that are multivalent, and so our first step will be to determine their ionic charges. As before, we will determine their ionic charges by first identifying the ionic charge on the anion. In the third example here, FO4 has an ionic charge of 1 negative, and that comes from practice and learning some common polyatomic ions. FO4 1 negative is based on FO3 1 negative, which is called fluorate. Since FO4 has 1 additional oxygen atoms, we call it perfluorate. Because it has a 1 negative charge, we can see that iron must have a 3 positive charge in order for the sum of all the charges to add up to 0. And now that we've identified the charge on the iron, we can incorporate it into the name using the IUPAC system as iron 3 perfluorate, or using the classical system as ferric perfluorate. Finally, in the last example, we can see our polyatomic ion looks somewhat similar to phosphate with 2 fewer oxygens. Even though it's lost some oxygens, perphosphate still has an ionic charge of 3 negative, which means that in this case, tin must have a 2 positive charge, and this gets incorporated into the name as Roman numerals in tin 2 hypophosphite, or classically as Stan-Us hypophosphite. When writing the formulas for tertiary ionic compounds, we can either use the zero-sum rule or the crisscross rule, just like when we were writing formulas for binary ionic compounds. In our first example, if we spend a moment looking at the name, we can see the 2 parts of this compound are barium ions and iodate ions. We need to know their charges. Barium is a family 2 metal with a 2+ ionic charge, and iodate is a polyatomic ion with a 1 negative ionic charge. Using the zero-sum rule, we would ask how many of each of these ions do we need for their sum to equal 0, and we would find that we need 1 barium ion for every 2 iodate ions. That would give me the formula of Ba1 and then IO3 twice. And because I need 2 of the entire iodate ion, I have to make sure I use brackets. If I wanted to use the crossover rule instead of the zero-sum rule, I would do the same thing I've done in the past, which is to take the magnitude of my ionic charge and cross it down, and these numbers then become the subscripts in the formula of my compound. However, I still need to remember to use brackets for my polyatomic ion, since I have more than one of them. And one final example here, chromium 2 carbonate. I know what my cation is. It's chromium with a 2+ charge. And carbonite will be based on the carbonate ion, although it will have 1 less oxygen atom. So it will be to CO2 with a 2 negative charge. And I can use the zero-sum rule to identify I need one of each for the sum of the charges to be 0, or I can cross down and reduce to realize that the final formula of my compound will be CrCO2.